This is part B for the review for final. We're gonna continue with chapter 4, 4.1 area between curves. So a picture here of a function f from a to b. We know, well, first this area under the curve and then between curves. So we know that the area of the region, the shaded region, is equal to the definite integral from a to b, f of x dx, which is equal to a number. So 4.2, we talk about the definite integrals and properties. In 4.1, we approximated that area with sum of areas of rectangles by dividing the region into strips of rectangles, adding them up, taking the limit, and we saw the limit of that Riemann sum is the definite integral. So in 4.2, we had some properties, and I'm going to write down some of them here. Integral from a to b, f of x dx. If you want to switch the boundaries, you have a negative sign on the front. Also, definite integral from a to b of a constant. If a function is a constancy, then straight line, then the area is length times width. So c is the height, b minus a is the length of the rectangle. 4.3, fundamental theorem of calculus. Fundamental theorem of calculus, part 1. Says that if f is continuous on the interval from a to b, then the function g of x equals integral from a to x, f of t dt is an antiderivative of f. What that means is g prime of x is exactly f of x, and x is between a and b. Part 2, we also know it as the evaluation theorem, and that's what we use when we evaluate definite integrals. It starts with f being continuous on an interval, then integral from a to b f of x dx is equal to capital F of b minus capital F of a, where big F is any antiderivative, where big F is any antiderivative of little f. In other words, big F prime is equal to little f. So example, if g of x is equal to integral from 0 to x square root of 1 plus t to the third dt, and we want to find g prime of x, that's d dt of this function, g of x. So what we're doing here, we're integrating then differentiating. And so that's the part 1 of our fundamental theorem of calculus. The integration, differentiation are inverse processes. So we're doing something and doing, then we are back to the original function, 1 plus x to the third in terms of x. So a function in terms of x, because it says here, g of x, then you have to be in terms of x here. All right. Another example, where h of x is equal to integral from 2 to 1 over x sine to the fourth t dt. Now, what's the difference here? We still need to find the derivative. The difference here, I want you to notice something. Let's use this color. In our first example, we had the upper bound just x, okay? And in the second example, we have a function of x. So if that's the case, we need to use a substitution. U equals 1 over x then du dx is equal to negative 1 over x squared. So when we find our derivative, which is d dx of integral 2 from 2 to 1 over x sine to the fourth t dt, I'm going to use a substitution. So instead of d dx, I'm going to do d du first. So now from 2 to u, sine to the fourth t dt, and then du dx. So notice now that we have u here and u here, they're matching. So we can apply the part 1 of fundamental theorem of calculus, where it say if you integrate and then differentiate, you're back to your original function, which in our case is sine to the fourth of u. Okay, so we're keeping u and then du dx. Now substitute u with 1 over x, sine to the fourth, 1 over x, and du dx is right here, negative 1 over x squared. Now, you have to be careful not to simplify here because there is nothing to simplify, but I'm going to put negative 1 over x squared on the front. Do that here. Negative 1 over x squared on the front, sine to the fourth, 1 over x. So that's it. All right, 4.4 indefinite integrals. Formulas. These formulas actually come from chapter 2, differentiation formula. So integral of c times f of x dx is equal to c integral f of x dx. So the constant goes on the front. That works for definite integrals as well. Here's our power rule. Integral of x to the n plus 1 over n plus 1 plus c. Integral of sine of x dx. It's negative cosine x dx. There's no dx here. Negative cosine x plus c. You can always check those formula by differentiating. So integral of cosine x dx, that is just sine of x. Integral of secant squared x. Well, that's the tangent. Integral of cosecant squared dx. That's negative cotangent. And 2 more, integral of secant x, tangent x. So if you know your differentiation formulas, then you know the integration formulas because they're opposite or inverses of each other. And the last one is integral of cosecant x, cotangent x. That is negative cosecant x plus c. So example, integral from 1 to 9. And here I have a rational function, 2t squared plus t squared square root of t minus 1 over t squared dt. We don't have a formula for integrating a rational function, but this is a special one. We could actually split it down to several functions by dividing by t squared each term, like this. And I'm going to write t to the 1/2 instead of square root of t. Okay, so after we simplify here, we're going to have 2 plus, all right, so 2 and 1/2, which is 5 over 2, minus 2, 2.5 minus 2 is negative 1/2, minus t to the negative 2 dt. Okay, I'm just going to give you the answer here. You can practice evaluating each one separately. 32 and 4/9 is the answer. Another example where I have a product and we don't have a formula now. In Calc 2, you're going to learn integrating by parts, which is sort of the product rule for integration, but here we don't need that because we can FOIL and then integrate. So do any algebra you can think of first to make simple the integrand. So 2u squared plus u plus that would be plus 9u plus 4. And then each one, when you integrate, you're going to have 2/3, u to the third plus 9 over 2, u squared fuss for you. And don't forget the constant at the end. And then we learn other techniques, the substitution rule. Okay, the substitution rule, which I used earlier. Symmetry. So if f is even function and I have integral from negative a to a, even function on a symmetrical interval, think about what even function, how about the parabola from negative a to a, f of x equals x squared. So definite integral, we're talking about this area. It's symmetrical, they're both the same, so I can just say that's 2 times 0 to a f of x dx. So it helps with integration. If you have integral that starts at 0, it's easier to evaluate versus negative a to a. So it helps simplify things. But here's something more important. If f is odd and I have to integrate that function in a symmetrical interval, let's see an example here. An example here would be, all right, f of x equals x to the third. This is the cubic function. So from negative a to a, these regions are the same, but one's underneath, so it's negative. The other one's positive, so they cancel each other, and that's 0. So very important to keep in mind, pay attention if your function is even or odd. That can simplify things. Example, integral from 0 to 1, v squared cosine of v to the third dv. We're going to use a substitution technique here. We're going to set u, a new variable, to be v to the third. And then we have a choice, either to change the boundaries with the variable, which I prefer, so we don't have to go back to the old variable, or not, but then you have to go back to the old variable. So if v is 0, u is 0, and if v is 1, u is 1, it just happened that they're the same. They didn't change. So v squared, and then cosine of u, and then what is dv? So we need to finish this. Du is equal 3v squared dv. So dv is du over 3v squared. Okay, so instead of dv, we're substituting du over 3v squared. So you always have to cancel the old variable. If it doesn't, then something's wrong. You have to go back and use a different substitution or check if you've made a mistake. So this is what we have. We have 1/3 cosine u, which is a very easy integral to evaluate. I forgot the du here. So integral of cosine u is sine u, and evaluate from 0 to 1. So 1/3 sine 1 minus sine 0. Sine 0 is 0, so it's 1/3 sine of 1. So here we use the substitution technique. Going to chapter 5, 5.1, area between curves. So if I have two curves, f and g, but from A to B, f is above g, and we're talking about this region. We want to find the area of this region. It's an unusual shape. We don't have a formula from geometry, but we do have a formula from algebra. So we have definite integral from A to B, always the top function, f of x minus g of x dx. If they happen to intersect each other from A to B, then you're going to break the region into two regions. So very important to write down here, f of x is greater or equal to g of x for every x between A and B. So again, if those functions intersect each other like this, from A to B. Then we're going to have this area first and this area, calculate them separately. Now, what if the region is such that the curves are from the left and from the right? So here is a picture where one curve is here and the other one is here. They're not functions. So this is f of y, this is g of y, and now from C to D is where our region is. So we want to find this area. But in this case, the left and the right boundaries are curves. So again, we can find the area, definite integral from C to D, the right function, oh, it's not a function, the right graph, f of y minus g of y, everything is in terms of y here. All right, 5.2, volume. So we approximated volumes with volumes of cylinders. We sliced, let's say you had a loaf of bread, we sliced it and each slice was approximated with volume of a cylinder. So the formula is for the volume of such solid, if you slice it from A to B and the cross section is A of x dx, then evaluating this integral will give you the volume. Or if you're slicing it, you always slice with a plane perpendicular to the rotation, to the axis of rotation. So if you're slicing vertically or horizontally, use one of those formulas. The cross section here will be A of y, everything in terms of y. So AX is the area of cross section. Okay. So if the cross section is a circle, then we know the equation for a circle. Then AX is equal to pi x squared, where x is the radius. If it's a ring or a washer, then the area is pi r2 squared minus r1 squared, where r2 is the outer radius, r1 is the inner radius of the ring. So this is our first method for finding volume, where the cross section is either a circle or a washer. Now sometimes we use a different method called volume of cylindrical shells, the method of cylindrical shells. And usually we use this where your solid has a hole inside. So we approximately this solid with nested cylindrical shells. And our formula for volume of the solid is integral from A to B 2 pi x f of x dx, which we like to remember as circumference. F of x is height if the solid is resting on the x-axis, and dx is the thickness of your shell. And this is the formula we use if the axis of rotation is vertical. So yeah, the formula is volume equals from C to D. Now 2 pi y f of y dy if the axis is horizontal. This is the case when the axis of rotation is horizontal. So if it's horizontal, we have dy. Here, if the axis of rotation, we're rotating the region. If axis of rotation is vertical. So it's kind of ironic, but vertical axis, we have dx. Maybe I'll do this. Vertical axis, dx. Horizontal axis, dy. And this is for this method, cylindrical shells. Okay. 5.5. we had a formula for average value of a function. So we know how to find average value if you have a list of numbers, but the function being continuous, think about the temperature that changes all the time. So no matter how often we take the temperature to measure it, we cannot measure every single one. So nevertheless, we have that formula, which is the definite integral, which is area under the curve of our function divided by b minus a. And then we had another theorem called mean value theorem for integrals that says that if f is continuous on some interval from a to b, then there exists some number c in the interval such that f of c, the value of the function, that point c, is equal to the average value of the function. In other words, think about the temperature again. If the average temperature is, let's say, 34 degrees, is there a particular time in a 24-hour period where it reaches? Yes, at least one. So here to illustrate this with a picture, if this is our function f, think about the temperature from A to B, and the average value is somewhere here. This is f average right here. Is there a point where the value at that point from A to B is equal to that? Yes, here's one and here's another. So this is the point C2 and C1. So there is at least one. And then chapter 6, we talked about inverse functions. It was mainly review. We talked about review one-to-one function. One-to-one function is a function whose inverse is also a function. So we want to work with one-to-one functions because the inverses will be a function. So how do we recognize them? Well, we do horizontal line test to test if the function is one-to-one. And we also reviewed how to find the equation of the inverse using the 4 steps. We also had cancellation equations. So the inverse of f, these two are inverses of each other, so you go back to x, and if you do it in that order, it's still x. So this is the cancellation equations. 6.2, exponential functions and their derivatives. Exponential functions and derivatives. Okay, a quick review of the exponential function. F of x equals a to the x, where a, the base, is greater than 1. It's exponential growth. On the other hand, if the base a is between 0 and 1, then it's decay or decreasing. And we have this formulas. The easiest formula in calculus is the derivative of e to the x, which is the same. So then we practice this new rule with the chain rule and all the other rules. If y is equal to e to the tangent of x, how can we find y prime? So y prime will be e to the tangent of x. We repeat that. And then we have to multiply by the derivative of the tangent, which is the chain rule. So that's equal to e to the tangent. Derivative of the tangent is secant squared. And that's it. Then 6.3, we introduce the log functions, where we review them. Log functions and their derivatives. So the log functions are the inverses of the exponentials. So if I have an exponential here, and if I try to find the inverse, I know it's 1-to-1. We can see from the graph of the exponential that they're 1-to-1. Then that, when I solve for y to find the inverse, I have to introduce a new notation, the log notation. because otherwise I couldn't solve for y. So this is a logarithm, it's the inverse of the exponential. Then the laws of the logarithms, I'm going to write them down because we need them. Number one, if I have log of a product, that is sum of the logs. And the second rule, if I have log of a quotient, that is the difference of the two logs. And the third one, which we use a lot, log of a power. The power goes on the front. So these three rules we use a lot for logarithms, and we also have a formula for change of base, because your calculator has only two logarithms key, base e and base 10. So if I need to change the base, let's say this base is base a, and I need to change it to natural log base, that's ln x over ln of a. Or you can change it to base 10 log of x over log of a, either one. So the natural log is a log with base e. ln x is how we write the natural log, equals to y, then that's equivalent to e to the y equals x. So this is the same conversion equation but with base e. 6.4, derivatives of log functions. So we had several formulas here. The derivative of ln x is 1 over x, and also we proved the derivative of absolute value of x, ln of absolute value of x, is also 1 over x. So example, y equals ln of x to the third plus 1. We're going to use this new rule with the chain rule to find y prime. We do 1 over x to the third plus 1, chain rule, multiply by the derivative of x to the third plus 1, which is 3x squared. All right, and a few new formulas here with the base not e. So let's write all the formulas. The ones we know with the base e are easy. Okay, so the base e here, the derivative of ln x is 1 over x. That's what we know. Now, if the base is not e, but let's say b to the x, derivative is still b to the x ln b. So we make adjustments here. And log of x base b, this derivative is 1 over x ln b. So notice here, ln b is on the bottom, ln b is on the top. And lastly, review logarithmic differentiation. For example, if I have y equals x to the x, and we did this in our 6.4 lecture. So if you want to find y prime, how do we do this? We take ln both sides. We use the law of the logarithms, in this case the power rule, and then differentiate implicitly. So take d dx both sides. So on the left side, 1 over y, but y is a function of x, so times y prime. And here you're going to do the product rule. Derivative of x is 1 times ln x plus x. Derivative of ln x is 1 over x. So we see this cancel, and we have 1 over y prime equals ln x plus 1. Y prime is y ln x plus 1. And finally, substitute y with x to the x. So the only way to differentiate functions of this type, which is f of x to a power g of x, we don't have formulas, but we have to do logarithmic differentiation. All right, that concludes part B of the review.